We're in Chapter 17. This is pretty much divided into two parts, serological testing and vaccination. Okay. In the previous chapter, we talked about antibodies, lots of it. Alright, different ways you can get them. You can get a disease and get over it. Once your immune system has responded, you now have antibodies. We can take antibodies from somebody or something, an animal, a horse, that has already been exposed to the antigen or had the disease, and give it to a person. That's called passive transfer. Or we can purposefully give the person, expose the person to the antigen and let their own immune system respond, and that's immunization. In all cases, you are providing immunity to a population. Different ways to go about doing it. Generally, it's done either by the disease spreading through the population or by vaccinating a population. That is called herd immunity. So you see a picture over here about herd immunity. Get my picture a little bit higher here so you can see it. Alright, so up at the top, look at the people in blue. You've got a population of, 40 people there or so. And you can see that there are a couple of people in red that are ill. They have the disease. But the rest of the population is healthy, but they are susceptible. And as a result of the two people that spread the disease, the rest of the people get the disease eventually. Now look at the bottom, and you see a situation where there are two people with the disease, as in the first scenario. You've got 4 people that have not gotten the disease. They are susceptible. But then you've got a lot of people that have been vaccinated. They've been immunized. And those people form a barrier in which the organism cannot easily spread to the people in blue. That is, the people that are susceptible but have not yet gotten the disease. So basically you have placed immunized, resistant people as blockers to reduce the transmission of the disease to the susceptibles. Every disease has a certain herd immunity percentage. So for example, in a classroom, in a college, the herd immunity against, tetanus, let's say, would be very high because you have to have a tetanus vaccine probably to get into college these days, or at least high school. On the other hand, the herd immunity against, Lyme disease would be very small. There is no vaccine for Lyme disease, and most people haven't had Lyme disease, and so the herd immunity would be very small. Okay, sometimes you want to measure antibody. The area that we're in is called serology. It's the use of antigen-antibody reactions for diagnostic purposes. Why do you want to know this? The obvious reason is to determine whether you've had an infection or how long ago it's been. Second, serological testing is done to determine a variety of autoimmune disorders like lupus, or whether a vaccine has been successful in boosting your immune response, or whether you do need to get a booster vaccine. So I'm going to talk about this in more detail in class, so I don't think I'll go into the pictures here. I've got a picture up at the top right showing how titer is done. Antibody titer is just the concentration of antibody in the patient's blood. You are analyzing the serum concentration of antibody. And the more you can dilute out the patient's serum and still get a reaction with the antigen against the antigen, and it depends, you can do different kinds of antigen antibody tests using different kinds of antigen. The more you can dilute out the patient's antibody and still get a reaction, the higher the titer is. And as you can see, titer is given as a fraction, 1 over 20, 1 over 640. So if patient A has a titer of 1 over 640 to, let's say, tetanus antigen, and patient B has a 1 over 20 titer against tetanus antigen, the larger titer number would be 1 over 640. That person A has a much stronger immune response to the tetanus antigen. Titer is used to diagnose disease. On the bottom, you see a look at titer against pertussis or whooping cough. And you can see a dotted line going down through the middle, black. To the right of that is high titer. That's diagnostic for people having pertussis. Low titer. Towards the left, not significant amounts of antibody, therefore a person does not have pertussis. Okay. Obviously, there are different ways to identify antibody. We're going to be talking about different antibody tests. And there are differences in the patient's antibody immune response. Individual factors. For example, if you're protein malnutritioned, you're just not going to have a strong immune response because antibodies are, of course, protein. Or if you have had exposure to the antigen before. Maybe you've been vaccinated a couple of times with hepatitis B vaccine. You know, there are 3 doses that you're supposed to get. More exposure, stronger the response. The larger the dosage, exposure, the greater the immune response. The picture you're looking at here is showing you primary versus secondary immune responses. So on the left is first exposure to the antigen. You can see that IgM is made earlier than IgG. Here's your exposure time right there. But IgG gives you a much stronger response. And a lot of tests are based on IgG levels. Some tests are based on IgM. But look at the green line, which shows you total antibody. Well, look at your second exposure, or it could be third exposure, fourth exposure. The more exposures, the greater the immune response. Look at IgG. It really goes up, and it goes up quickly. So, with every exposure to the antigen, whether you get the disease or whether you get vaccinated, because there are a lot of vaccines that depend on boosters, the more often you're exposed, the stronger your immune response. By the way, that secondary immune response is due to memory cells already being exposed and very ready to turn on when they see the same antigen. Now, what you're looking at here is the difference between active and passive immunity. Active means that your own immune system has come in contact with the antigen. Look at the red line. So here's your first exposure. Again, let's say this is a vaccination. Here is a second exposure. Here's that secondary immune response. This was primary immune response. Here is another booster vaccination, and you really get a strong secondary immune response there. Again, it could be due to you getting exposure to the disease antigen 3 times. Also, either immunization or by getting the disease. Now look at the green line. This is if we give the person pre-made antibodies. So the person's own immune system has not come in contact with the antigen. Their own immune system has not responded. They are being given antibodies from either other people or very often horse antibodies are given to people. Horses have a huge blood supply. You can inject them with an antigen, they make antibody, you purify it, you give it to people. Passive antibody is given after exposure. Active immunization and acquired immunity, like vaccines, is given before exposure. Obviously, that's a better way to go. Besides, remember, once your immune system responds, it will remember via memory cells. When you're given passive antibodies, because your own immune system does not respond, it doesn't identify that antigen a second time, a third time, and so on. Okay, here's just a look at an important historical perspective on immunization. The common disease that's always used to illustrate this is smallpox. It's pretty much the only disease, infectious disease, that's ever really been eradicated totally with immunization. One reason why it was so successful is because in the world of smallpox, if you had been exposed to smallpox, you were always symptomatic. You always had the symptoms. And they're very obvious symptoms. It's not like flu where you can have a mild case and you don't know you have flu and other people don't know you have flu. In the case of smallpox, when you got the disease, you got the disease. Everybody knew it. You knew it. So, because it's so easily identified, the symptomology, it's just much easier to control, to immunize, and then follow the how many cases there were. And you could find people that had been exposed. So this goes back to Chinese, through Chinese history, 2000 BC. The disease that they were vaccinating against was actually smallpox. Again, these are the pictures that you see, particularly the little girl on the left. This is a viral infection. It produces extreme lesions that you see all over her. And when these lesions healed up, if she did not die, you got a scar. It was a very obvious scar. So it was very obvious from seeing these people that they'd gotten over smallpox if they did not die. The Chinese thought that it would be much better if you could actually give people smallpox, a mild case, and hopefully they survived, and then if they got over it, they had a lifetime immunity. Now realize they knew nothing about viruses, they knew nothing about infectious disease, nothing about vaccine. They were doing it blindly. They just knew it worked. Again, some people died, but that was a small price to pay. Now, if we forward to the latter 1700s, Edward Jenner had known about a variation of this variolation. By the way, the name for the smallpox virus is the variola virus. So in the latter 1700s, he is responsible for coming up with a more controlled way of immunizing, but he wasn't using the smallpox virus. He was using vaccinia virus, which is the cowpox virus. People got it from touching the udder of cows. Milkmaids, for example, got a very mild case of vaccinia virus. on their hands, and once you were exposed and your immune system reacted against cowpox virus, you had a cross immunity to smallpox virus, and you never got smallpox. So his idea then was to vaccinate people against cowpox. Now remember, even at this time in the latter 1700s, nobody knew squat about viruses at all. They were still doing it blindly. So the picture you see here, you're looking at a cow upside down on a board. They are purposefully exposing the cow to cowpox, extending it all over the bottom of the abdomen that's been shaved. They would produce these large lesions of cowpox all over the bottom of the abdomen. They would scrape these lesions off with zillions of viruses in them. And then they would grind up the virus material and use it to inject into people's bodies. And you see a look at this right here. So again, you're looking, in this case, at the bottom. Look at the bottom. You're looking at vaccination, what the lesions look like over time. The view above is actual smallpox. But again, in both cases, you can see the lesion scars. And if you ever run into anybody even now that's had a smallpox vaccine, which, by the way, in the United States they stopped in the latter 1970s, they would have a vaccination scar. But again, remember they used cowpox, not smallpox virus. So, vaccination. What about it? Well, obviously there are some problems, real, some unfounded. There's been a worldwide initiative to get rid of polio in the last, 15 years. It's been very hard. There's still hot spots of polio in certain areas of Asia and Africa. Polio, there have not been many natural cases of polio in the United States for years because of the vaccine. Everybody's vaccinated. Well, unless you have a religious reason or the Amish don't vaccinate or something like that. But in other countries, when developed countries try to send these vaccine lots to the countries that have polio, as you can imagine, because we have a history of maybe not treating populations well, or the countries well, they don't quite trust us. And so there's a lot of socioeconomic and political problems associated with developed countries trying to help underdeveloped countries. There's also fewer and fewer companies that want to make vaccines because of liability. There are some side effects. There have been some side effects of vaccines. Some of them real, some of them unfounded. Here's a look at vaccine types, different kinds. I think you might be able to make out the different vaccines if you make this a little bit larger. Let's go with killed. So if you look at the list here, whoops, let me point out some vaccines made of killed organisms. Look at typhoid, Salmonella typhi, killed bacteria. Rabies virus vaccine, cholera up here. No way to get the infection, totally inactivated, destroyed bacteria. Okay, second scenario. Active organism, but it's been weakened to the extent that it cannot cause a disease. This weakening is called attenuation. Examples, flu. The flu mist vaccine, by the way, is attenuated. It's got an active virus. By the way, the flu shot, and we've already talked about this, that is a totally inactivated viral preparation. But there are two kinds of flu vaccines. The flu mist is the one that's taken intranasally, and it's active virus. Another example, mumps, measles, rubella, what's called the MMR. Now you can get the MMRV, and the V stands for varicella, which is chickenpox. Tuberculosis attenuated vaccine. There is a risk, and the risk is that if you're immunodeficient and you get one of these vaccines, because you have no immune system, even though this is a very weakened organism, you could potentially get the disease. Third scenario, toxoid vaccines. There are only a couple. Diphtheria and tetanus down here. This is inactive toxin, exotoxin, no longer toxic, but still immunogenic. No way to get the disease. Then there's subunit vaccines. These are very often made by genetic engineering. For example, look at the HIV vaccine. This is Haemophilus. Used to be the #1 cause of childhood meningitis, bacterial meningitis. It's made of the polysaccharide capsule of the bacterium. The gene has been identified. The gene is inserted into E. coli. The E. coli makes this polysaccharide capsule material. It is purified. You use it in the vaccine. You're injected with it. You make an antibody against the capsule. If you ever come in contact with this particular capsule for Haemophilus, you are protected. Your immune system has already seen it. Another example is a meningitis capsule or vaccine. DNA vaccines. New kid on the block for vaccines. I'll take you through one in a minute. Let me get rid of all of these things. Okay. Well, let me go ahead and take you through somewhere. Here we go. Here's a DNA vaccine, kind of interesting. Here's the case of HIV. Oops, didn't mean to do that. Alright, here's a case of HIV. So here's our HIV. We pick out a particular gene or genes that we want out of the genome. We stick those genes into a plasmid. There you go. We make lots of copies of the plasmid. We inject it into muscle of a human. Here's the plasmid right here. Here are the HIV genes. Now remember, you're not using whole HIV. You're not going to get HIV. This is only a gene or a couple of genes. For example, for making a protein capsid. The muscle cells see this new HIV gene. They make the protein. Your muscle cells do. This protein is foreign, correct? Your immune system has never seen it before. It alerts your immune system. You make antibody. You get turned on B and T cells. If you ever in the future come in contact with a real HIV, your immune system has already made preformed antibody to HIV. Can you see why this is a DNA vaccine? Okay, let me go back again here. Okay, so what do you want in a good vaccine? I think all of this is probably self-explanatory. Let me talk about adjuvants. Very often, because the antigen is not really strong enough to cause your immune system to mount a strong response, they have to add something to heighten the immune response called an adjuvant. Wanted to mention that because I'm sure all of you have had a tetanus vaccine. It's given into the arm. A day later, your arm hurts like hell. It's not because of the toxoid, which is the manipulated exotoxin. It's because of the adjuvants that are added and cause a slight inflammatory reaction. Here's a look at what's happened to cases of rubella, which is German measles, red measles, polio, mumps since the vaccines were introduced. Um, where are we going? Well, there's been some advances towards tumor vaccines where they take tumor cells out of your body, create heightened immune cells that are exposed to your tumor cells, and then put those cells back in your body to tell your own immune cells to turn on. Those are called tumor vaccines. Also, combined vaccines may be in the works where they combine many antigens at one time. They already do that for flu now. They use 3 different flu strains in one vaccine. That way you wouldn't have to get all of the different vaccines that are required when you're a child. I talked a little bit about some side effects. I gave you an example of tetanus and your arm hurting. I guess you could call it, it's not really toxicity because it's the adjuvant rather than the toxin. Again, possibility of you getting the disease if you're immunosuppressed. Some people have an allergic reaction to a vaccine. That's not due to the vaccine material, it's due to an idiosyncrasy of your immune system. And that can be a very severe reaction. We'll talk more about that when we get into the next chapter, chapter 18 actually. And then again, lots of anecdotal evidence, where one person claims that their kid or they had a reaction, but we don't have any data on it. We don't even know if it's true. So again, some problems with getting data that's factual. I mentioned passive giving of antibodies. This is done, interestingly enough, for things like spider venom once you've been bitten, for certain snake bites, cobra, rattlesnake. Antibody gives you very fast protection, but again, you have to get this antibody very quickly. So these are, again, preformed antibodies, either from humans or from horses, usually, again, made in horses. Okay, so I'm going to do a second video taking you through some information on antibody tests. So this is where I'm stopping.